Hi, my name is Ariana Rodriguez, and I'm going to show you how I did my Fluent 2D flow simulation of air over a flat plate. This is Project 2 for Professor Osbay's Summer 2026 Fluid Mechanics class. So I'm going to open my workbench, going to start with a fluid flow Fluent project, click and drag it over to create a new system. I'm going to select 2D geometry, and then right click, New Design Model Geometry. So wait for that to open up. Perfect. Click on the Z-axis since we're working 2D. Sketching, we want to sketch a rectangle. So click on the origin, drag out, and for this, we were told it is 100 centimeters is the length. So 100 centimeters is 1 meter. So I'm going to go over here to dimensions, set the horizontal length first. Awesome. Oh, and by the way, units are in meters, but if you want to change them, you can change them there. But I'm just going to keep mine in meters for simplicity. And then vertical. For mine, I'm going to make the vertical 0.05. Awesome. So if we back to modeling, if I zoom in, here we go. We can see our geometry. So I'm going to click over here on the sketch. You can see it's selected, it's yellow, and it'll be concept, surfaces from sketches. And I want to apply the selected, apply, perfect. So now we have our surface sketch here, and we can now generate our mesh. So perfect, it is, or generate our shape. So now that it's shaded in gray, that means we're ready to move on to the next step. I'm just going to click save over here. And while that saves, and then I can close out and go to the next step. So the next step here is the mesh. So I'm going to double click that. Sorry, my computer is a little slow with opening and loading everything. Awesome. Okay, so we have our geometry here. Under mesh, I'm going to click insert, face meshing. And then, oh, I want to select a face to do the face meshing. Um, so apply selected face. Awesome. And then generate. Great. So now if we click here, we can see our mesh is created, but doesn't really tell us much. So we want to now go onto mesh, insert sizing, and gonna control click the top. Oops, sorry. Edge click top and bottom. I'm gonna hit apply, so we just want the top and bottom selected. We're gonna do the type of to number of divisions, and I'm going to do 50. Capture curvature becomes no, and you want the behavior to be hard. So that looks all good. I'm going to generate. And so now if we go to mesh, we can see here that it's generated. Because we're working with a horizontal flat plate, that'll be on the bottom. So we kind of want our mesh to be more fine towards the bottom and less fine towards the top. So I'm going to right click, insert sizing again, make sure that our edge is selected. We're starting with the inlet. So I'm going to hit apply. It's going to be by number of divisions, and I'm going to make the number of divisions 60. Capture curvature, no. Behavior hard. And so since we want more fine meshes towards the more fine meshing towards the bottom, we are going to have to apply a bias here. So I'm going to select this one and the bias factor, I'm going to make it 70. So if you see here, if I were to zoom in, the divisions are more fine towards the bottom and then more spaced out towards the top. So that all looks good. I'm going to generate. Awesome. So you can see here, kind of looks a little funky, but just because we haven't done the other side yet. So I'm going to zoom out and follow the same process essentially for the other side. So make sure that my edge is selected, insert sizing, perfect, apply. The type is going to be number of divisions. I'm going to do 60. Capture curvature, no. Oops, no. Behavior, hard. Bias type, like this, perfect. And we're going to do the bias factors, 70. And now I just want to confirm again. If we zoom in, oops. But here it shows that the top is more fine than the bottom. So we actually want to reverse the bias. So we're going to select on this side again, apply, and now we can see that it's flipped. So now I can generate the mesh. Awesome. And now, perfect. We can see our mesh is generated where it's consistent and the top is more spread out, or I guess the cells are larger, and it's a lot more fine as we get closer to the plate. Great. So our mesh is complete, and now we just want to name everything. So I'm going to go to mesh, insert. Oh wait, no, that's not what I'm going to do. I'm going to click on the edges. So I'm going to select the top, right click, and then create name selection. So I'm going to name this one far field. Okay. The bottom, which I can just press N, is going to be the plate. The inlet. And now my outlet. And perfect. And then I want to select this face. I'm going to hit N, and then I'm going to name this one airflow. Awesome. And we can see all of those here. So I have my far field at the top, plate at the bottom, inlet, outlet, airflow. Great. So now that we have our meshing and our name selections, we are ready to move on to the next step. I just like to hit save up here, and I can close this. Need to give it a moment. Perfect. And I just want to make sure it's updated. So right click update. Wonderful. All right. So now we can go to the setup. I'm going to select double precision. Solver processes, change that to 2 and start. So while this opens up here, I'm just going to briefly see the conditions. So it's a velocity of 2 meters per second. The air density is 1.2 kilograms per meters cubed. The viscosity of air is given as 1.8 times 10 to the negative 5 kilograms per meter second. Viscous flow study. Okay, great. So we just need to let it fully load up. Wonderful. So we can see our mesh over here. Okay. And then our inlet and outlet fields. So I'm going to start over here, models. I want to select viscous and I want to make this a laminar flow. Everything there. Okay. Under materials, want to select air. We're going to change it to 1.2 because that's what the question's asking. And this one is 1.8 times 10 to the negative 5. Constant 1.28. Change slash create. One more time and then close. Okay. Just want to confirm airflow, which I can see there, fluid airflow. Okay. Close. Now I'm going to go to boundary conditions and establish. So we have our far field, which we said was the top. I'm going to change that. Instead of wall, it should be symmetry. Inlet is velocity inlet. And double click inlet. It's going to take a moment to open up. Wonderful. I want to change the velocity to 2, like how our question was asking. Apply, close, interior airflows and interior field. Good. Apply, close. Outlet is a pressure outlet. You just want to make sure prevent reverse flow. Just make sure that's selected. And then the plate is the wall. I'm just double clicking to make sure everything is, yep, stationary and no slip. So now our boundary conditions are all set up. We can see them over here, our inlet, outlet, symmetry, far field, and our walls are plate. Great. Now I just want to double check our reference values. So we're computing from the inlet. Reference zone is our airflow. So our density is 1.2, velocity is 2, viscosity is 1.8 times 10 to the negative 5. Okay. Now I want to go to methods. I want to change the scheme to simple. You don't have to worry about changing anything else. Under controls, don't need to change anything here. Monitors residual. You want to add 2 zeros, so it ends up making it 1 to the negative 5 for all values. Hit OK. And now that should be everything. We should be good to initialize. So instead of hybrid, it's going to be standard initialization. We're computing from the inlet. I'm going to change the Y velocity to 0. Relative zone 2. Perfect. I'm going to hit initialize. I think we should be good. I'm pretty sure it initialized. I'm just going to do it one more time just to confirm that. 0. Perfect. Okay, now we go to run calculation and change the number of iterations to 10,000 and calculate. So I set it up for 10,000 iterations, but when I've done it before, it usually only takes up to 1,000 to do. So I'm gonna let that run a little bit. And then I will show how to find, let me see. I will show how to find the drag coefficient in the results section, and then I like to do the velocity profiles and contours as well as this one, the wall shear stress and skin friction in the results section. But all could be done here. It's up to personal preference. Great, all done. Okay, so to find the drag coefficient, it would be under reports. No, wait a moment. Um, reports. Oh, sources, calculation reports, report definitions, new. Force, drag. There we go. So it's under solution, report definitions, and then forces, drag. So now we want the drag coefficient for the plate. I'm gonna hit compute, and then we can see if I hit OK. Perfect. So here is our drag coefficient of the plate. So now I'm gonna go close out of this, and I will find the rest in the other section. Great. So the first part was asking for the contours of the velocity with vectors, and then also the pressure. So I'm going to click Z-axis here. Let me maximize this window. Contours, velocity contour. Okay. Location is going to be symmetry 1, velocity U, and number of contours. Apply. Great. And then going to adjust the legend. Horizontal. Next. Awesome. And then I will add my vectors. So it'll be velocity vectors. Okay. And I'm just going to unselect my contour just so I can have a better view of my vectors when I'm working on them. So location will be symmetry 1 again. The vertex, no. Velocity. Awesome. So I'm going to hit apply. And so arrows are a little funky, so I like to adjust them. So I'm going to go under symbol, 2D arrow, and I'm going to change the symbol size to 0.2 and hit apply. So now if you zoom in, you can see the arrows. And then we're asked for the velocity vectors with the velocity contour. And let me go to the velocity contour. We can change the transparency to get a better view. So I'm going to change the transparency to 0.6. There we go. So now we can see our contour and our vectors. And we can see here that this is the boundary layer. Awesome. And I'm just going to, I think this is a good view of it and it shows everything. Perfect. So now I want to create my pressure contour. So I'm going to say pressure contour. Perfect. Symmetry 1. I'm going to unselect my vectors and my contours or the velocity just so I can see the pressure a little bit better. Pressure, global. There we go. And now this is our pressure contours. So next, I want to plot the velocity profiles at x equals 35 centimeters and x equals 75 centimeters. Okay. So I'm going to just go back to my velocity contour, unselecting my pressure contour. Great. So to find them at different locations, I'm going to insert a line. I'm going to say this one is x35. So now our x is going to be at 0.35, 0.35, and I want it to span the entire height, and I want to do 100 samples. So I'm going to hit apply, and we can see here, this is our yellow line, showing that the values are measured at 35 centimeters. So now I'm going to insert another one for 75. So insert line, I'm going to name this one x75. Okay. 0.75, 0.75, and again, spanning the entire height. So if you didn't make your 0.05 meters, you would just put whatever height you ended up choosing. Apply, and now we can see here that is our sampling at 75 centimeters. So now I want to insert a chart. So I'm going to call this one velocity profiles. Okay. I'm going to title it velocity profiles. The data series will be x equals 35 centimeters. And the location, that one is x35. I'm going to add a new series, x equals 75 cm. And that one's going to be x75. Awesome. Our x-axis is going to be our velocity, u, and our y-axis is just going to be y. Okay, I'm going to hit apply. Great. And so now we have our velocity profiles here, and we can use this to help us find our boundary layer thickness. Alrighty. Next is plotting the wall shear stress and skin friction coefficient. Okay. So going to select chart. So wall shear stress. Okay. I'm going to name it, title it wall shear stress. The data series, oh, actually, let me go back. I have to establish a line. So I'm just going to apply that for now, just to hold on to this. But we want it to be along the plate. So I'm actually going to insert a new location line, which will be, I'm going to name plate. And it's going to go from 0 to 1. And perfect. This is the line. Do 100 samples again. So now if I unselect my velocity contour, we can see we have a yellow line going all the way across that spans the length of the plate. So now if I go back to editing my wall shear stress, my data series takes place at the plate. I'm going to wall shear stress. My x-axis is going to be x, and my y-axis is going to be wall shear. Apply. Great. So we have our wall shear stress. And now if I wanted to do the skin friction coefficient, we can see here it's actually not a variable, so you would have to make it yourself. So what I'm going to do is go under expressions, right-click expressions, new. And I'm going to name this skin friction coefficient. And also just a heads up, if we did this in the setup, there is a variable for it, but I was struggling to export the data that way, so I decided to follow this process. So here we can define it. So we know that the skin friction coefficient is wall shear divided by, I'm going to make my parentheses, 0.5 times the density, which is 1.2, and then you have to add your units in brackets, kilograms per meters cubed times, and then since we're going to square it, since it's velocity squared, it's 2 times, whoops, 2 meters second squared, oops, meter second negative 1. There we go. Oops. And then this quantity is squared. So let me apply. Perfect. So now we have our wall shear defined. Let me make sure this might be better if I just do it like this. Okay, great. So now we have our skin friction coefficient, so we can go to our skin friction coefficient defined, so we can go to our variables. I'm going to select new, and I'm going to name it CF. And CF is tied to an expression, and that expression is the skin friction coefficient. So I'm going to hit apply. Great. So now we have our skin friction coefficient. So I would go to charts. I'm going to name this one skin friction coefficient. Title of this one will be skin friction coefficient. Our data series, skin friction. I guess I could have named it CF, but that just feels better. It's across the plate. X-axis is X. Y-axis is CF. So I'm going to hit apply. Awesome. So now we have our skin friction coefficient plotted with X. And as part of this assignment, we would calculate theoretical and compare both of the both are theoretical and calculated, or theoretical and measured solutions together. Let me see if there's anything else. And that appears to be it. So yeah, thank you so much for watching.